Welcome to 600X, often referred to as the Introduction to Computer Science and Programming. It's odd to have both of those terms in the title, but both of them are important. This course is going to be not just about teaching you how to program a computer, how to tell the computer instructions that it can understand. It's also going to be really important to create within you a capability to think computationally. So our goal is to let you become skillful at not only getting the computer to do something, but to do that thing that you want it to get it to solve a problem. By the end of this course, we hope that your first instinct when faced with any interesting challenge is to first think about how could I capture that challenge, that problem, in an algorithmic or mechanical description of steps, such that I could get the computer to do the work for me. If you can do that, it's going to give you a great deal of advantage as you face any kind of problem, and those are the skills that you're going to see throughout this course. Now, if our goal is to have you learn how to get a computer to do something for you, how to talk to the computer, how to think algorithmically, one of the questions we can ask is, so what's the computer going to do for us? What's it actually good at? That seems like probably an odd question. After all, we know computers can do a ton of things. But it's still important to go back to a very fundamental and basic point. What does a computer do? In fact, it does two things, and two things only. It performs some calculations, and it remembers results so that it can reuse them. Now, you'd say, okay, so it performs calculations. That seems fine. But what kinds of calculations? Well, it turns out that every computer comes with a simple set of primitive calculations, things that we call built-in. They're provided by the manufacturer as the basic elements that a computer can use. We'll see some examples of that shortly. If that's all we have, that's pretty limiting. So a key thing as we go through the material in this course is to learn how we can create our own methods for computing something, how we can capture a computational way of thinking about something in a manner that can be used by the computer, and to do it in a way whereby the computer can abstract that. By that we mean that the computer can figure out how to take what you tell it and turn it into something that it can now treat as if it were a primitive, something that was provided by the manufacturer, and reuse that throughout its computations. So, our computers are going to do calculations for us, using a set of built-in primitives plus things that we add. Now, you might ask, gee, is that enough? If it turns out that a computer can just perform primitive calculations, is that sufficient? Well, as I'm sure you already realize, modern computers can perform those calculations incredibly quickly. And so one question is, if we can do them fast enough, is that sufficient to do interesting things? Let's look at both parts of that. First of all, how quickly does a modern computer actually run? Well, let me give you a simple little thought example. If I were to take a little gooseneck lamp and put it right here, a foot above my desk, and I were to time things perfectly so that as I hit the switch on the lamp, I hit a key on my computer and started them both up at exactly the same time. In the length of time it takes the light to go from the lamp to the desk, your computer will execute 2 operations. That's amazing. It does 2 operations, 2 of those primitive operations, in the amount of time it takes light to go, basically a foot. Unbelievable. There's another way of thinking about it. Imagine I take a simple child's rubber ball, and I suspend it about 1 meter off the ground, and I drop it. And if I let it drop, by the time it hits the ground, assuming gravity behaves normally, your computer will have executed 1 billion operations. Unbelievable. 1 billion operations by the time the ball hits the ground. Now, that suggests that, in fact, these computers are incredibly fast. And even though they're computing very simple things, they're doing them incredibly quickly. They are. We said computers do simple operations. We also said that they have some storage. So how big is the storage inside of a computer? Well, every element of storage is called a byte. And if we were to assume that a byte weighed 1 ounce, I know bytes don't really weigh ounces, but just assume they weigh 1 ounce. Typical computer has hundreds of gigabytes of storage. And that says, if each one of those bytes weighs 1 ounce, a computer would be able to store the equivalent of 300 million tons of storage. Okay, they don't really store it that way, but you get the idea. Incredible amount of storage, can remember a lot of things, and incredibly quick in terms of doing the computation. So, that sounds really good. The question is, if they're only primitive operations, is that enough? Are these simple calculations sufficient? Well, they're going to do a lot as we see, but we're also going to see that they're not quite enough to do everything we'd like. And let me give you 2 examples. I'm sure all of you have gone to the World Wide Web to look up a piece of information. You've searched the web to try and find things that you'd like to know about. And the question is, if a computer is just doing this the straightforward way, how quickly would it search the web? Well, it turns out there are about 45 billion searchable pages on the web at the moment. If we assume that it takes about 1,000 words, or there are about 1,000 words per page. Some, of course, are much more than that, some are less, but about 1,000 words per page. And just for sake of argument, we're going to assume it takes about 100 operations per word to find the word on the page and to decide if it's the right thing. 100 is actually high. Let's make it a little bit less. Let's just assume it's only 10 operations per word. How long does it take to actually execute that search? Well, we can do the math. You can grind it through. You got 45 billion pages. You got that many operations. You know how quickly we're doing these actual operations. If you put it all together, what you find is it's going to take you about 5.2 days to find something on the web. That's a slow browser. That's not going to work very well. And that basically is giving us a hint that even with really fast computers, we have to be smarter. Let me give you a second example. Playing chess, something that's seen as a very difficult task. It's impressive that about 10 or 15 years ago, a computer program actually beat the world champion in a chess match. And one of the questions is, well, okay, is it just because the computers are really fast? Well, we can look at this two ways. In a typical chess game, there are about 35 moves at any one time. And so the question you could ask is to say, okay, if I want to have my computer program look ahead 6 moves, 3 moves by me, 3 moves by my opponent, how many different options are there if there are about 35 moves each? And the answer is about 1.8 billion different sets of the chessboard that I'd have to look at. If I can check each move out in about 100 operations per move, then that says it's going to take me about a half hour to actually look at each move. That's pretty slow. And this is pointing to a problem that we want to get at. And that problem is that, yes, computers are really fast, but we need good algorithmic design as well. To deal with interesting problems, we need algorithms that are clever, are intelligent, are smart about how they actually do the work. And that's a lot of what we're going to talk about during this term. By the way, we also said space is a big issue, and we got a lot of space in the computer. If you go back to the chess example, you can ask the following question. How many different games are there in chess? Experts will tell you there are about 10 to the 123 different chess games that are possible. Is that too big for storing in your computer? Well, there are only 10 to the 80 atoms in the observable universe. So we can't just store away all the games and look them up. And both of these are pointing to why we're going to use this course to actually learn about thinking algorithmically. Now, this suggests it's just a matter of putting together enough speed and enough smartness. But what can be a little bit more distinct and say, are there actual limitations to what we can do with the computer? And in fact, despite its speed and its size and the cleverness of the algorithm, our computer still has some limitations. Here are a couple of examples. First of all, there are some problems that are just too complex. We don't have enough speed, enough storage, and they may get tackled as things improve. But examples here would be things like predicting weather at a very local scale. I'd love to know what's exactly going to happen outside my window for the next half hour or next 3 hours. Size of the problem is simply too big for a computer to be able to model well enough and solve in a reasonable amount of time. It turns out some of these complex problems actually help us. Modern cryptography, the way in which information is securely transmitted across the net, relies on having some problems that are simply too difficult to compute and therefore too difficult to break the code. So we actually get some benefits about problems that are too complex. But as we're also going to see later on in the course, there are some problems that are just fundamentally impossible to compute, no matter how big the computer is. And some of those are really handy. Here's one example. Being able to predict whether a piece of code will always stop with an answer for any input. And by that, I don't mean just you run it and see if it stops. Being able to write a piece of code and then have some other piece of code inspect it to say, this will always work. It will always stop and it will always give us an answer. This turns out to not be possible to solve. And this is known as Turing's halting problem. And we'll talk briefly about that later on in the term. But it says that there are some problems that are simply too hard to solve, period. Nonetheless, in this course, we're going to start talking about how do we think algorithmically and get the computer to do interesting things for us.